So this is horrible. Mind you, you can still write papers about that. There's another paper this year at which claims to have reinvented something cool which suffers from exactly that problem, but yeah. This stuff still makes it through the reviewing process. But
so are you assuming that your f of x is a linear function?
So yes. Yes, sorry, that was implicit, namely that my function f of x is given by a sum of fairly simple functions. If it were not nice and additive, things would be a lot more messy. There are a lot of interesting techniques such as dual decomposition, which we may or may not cover in this optimization part right now. We might get back to this a little bit later, which allow you to deal with more general classes of functions. But here's a much simpler way of dealing with a problem.
Is that
Sorry.
Is that decomposition? No, I mean that's still fairly like broad. Because I mean in statistics in general, you have like least squares or something like this. You're just going to have some.
So least squares, for instance, would fit it perfectly. Poisson regression would fit it. Support vector machines work. Most of Markov models of various kinds, if you have several instances of the data, would fit it. So there's a very, very large class of problems that actually all fall into this category. But sometimes you have an interesting variable dependent structure. And this is where those dual decomposition methods may help you. But to just quickly show you how you can actually speed up this algorithm rather drastically, well, if you think about it, it's essentially the line search that killed us, right? Line search was a brilliant idea on a single machine because the expensive part was computing the gradient. Doing the line search is essentially a freebie. For MapReduce, each of the steps in the line search kill you. Doing the gradients isn't much more expensive. So if you remember our convergence analysis, we didn't really assume that we knew exactly the result of the line search. We just took this step that was given to us by the upper bound on the Hessian.
I think you maximum a minimizer or the t.
Yes.
But one or might not be the minimizer, so I'm a little concerned with the bond, iteration bond here.
So the thing is, 1 over capital M might not be the minimizer. That's true. Almost certainly it isn't. Almost certainly this is way too conservative. Because basically 1 over capital M tells us a very, very short step size to take to make sure that even if the function were to curve in the most bizarre way possible right now where we are, we wouldn't miss the minimum. Right? So this is about the most conservative thing that you can do. But that's precisely what we use in our convergence proof. Right? And that's exactly where we got this M over M log accuracy from. Okay, so why not just use it in the algorithm? Now there are better ways how to deal with this problem rather than what I just showed you here. And we're going to go and look at some of those algorithms later, next week. But there's nothing to prevent you from doing this. The smart thing is to look at this type of updates and possibly do one extra pass for a speculative line search with maybe 16 points around that proposed step size. And that may actually give you something that's fairly reasonable. That may be about the fastest you can do in practice. So you basically have only one extra line searchy type of operation in addition to this. So you definitely evaluate at that point. You need to your grid layout with line search, and if you make more progress with that, well, good on you. Okay, now let's take a 5 minutes break, also because the files in the camera otherwise get too big, and then we'll look at the Newton method, and then we can go home. Okay, so.